Okay, yeah. First, before to give you the screen, Melli, just a quick introduction about you. We now have Melli, which is a product manager at Oracle. She has a large experience with semi-structured and unstructured data management. She's focusing, if I'm not wrong, on graphs, Kafka, and big data, mainly these days. And you also enjoy a lot working with customers, helping them to solve their problems by using these technologies. And I must admit, I often send you emails to ask for things, and you always have the answer. So that's the best thing ever. If you have a question, get in touch with her. She will fix it. Okay, that's maybe not always, but she will do everything she can. Now, Melli, it's all yours.
Thank you, Jenny. And that's a very nice compliment coming from you. So, because I know you always ask the tough questions. So it's nice to hear that at least sometimes I'm able to answer. So hello, everyone. I'm excited to be here and talk to you about what is becoming a very hot topic among researchers and among practitioners about new insights you can get when you combine graphs with machine learning. And as I've been listening to the sessions today and yesterday, I just felt that this is such an appropriate forum for this because we had the machine learning day yesterday and we've had excellent sessions on graph this earlier today. And now I want to kind of try and explain how you can bring these two technologies together. So the topics I want to cover over the next 20 minutes or so, this is a half-hour session, is one, I just want to talk about what we mean when we say adding graphs to machine learning. And I'm really going to focus on the more basic aspects of doing this. In other words, what you can do today with various products that are available. Then I want to walk through some use cases that are particularly benefit from adding graphs to machine learning. And usual question of how can you get started. So I want to show a little bit about how you can actually work with graphs and how you can integrate that into your machine learning algorithms. At the introduction, Jenny and Emma were talking about both machine learning. They talked about machine learning. They talked both with property graphs and RDF graphs. This session, I have predominantly focused on property graphs. So I don't have much material on RDF graphs. I hope to do that maybe at a future session. So let me start with graphs and machine learning. So as you would have seen yesterday and in your, as you've been working with machine learning applications, you know that when you're starting work with creating a model, you have a lot of existing data. You create a model based on that data, and then you want to use that model for predictions. Like I think from an example yesterday, from a demo yesterday, you can create a model from various chest x-rays of patients suffering from pneumonia. And once this model is created and trained, when it encounters a new chest x-ray of a new patient, it can potentially predict or diagnose that this person has pneumonia or not. And the quality of your model depends on a variety of things. A few things it depends on is the features you select when you create this model and the algorithm that you're going to use when creating this model. And of course, machine learning has a wide range of use cases. So you have many different ways to build your machine learning algorithm. And if you were to use PL/SQL APIs to do this in the Oracle database, it might look something like this. You'll have this PL/SQL call to create a model based on a particular algorithm, here the classification algorithm, from data that is stored in database tables. And then you would use this model to make predictions. So you create your model and you use your model to make predictions. And here, this is an example of predicting whether a new customer will buy this particular product, in this case, let's say an insurance policy. So will a new customer buy this policy based on what you know about the behavior of existing customers? That's what this model and prediction what they're trying to do. So looking more closely at the features that have been selected to create the model and the features that are used to make predictions, these are the obvious, some of the obvious features that make logical sense: the age of a person, the marital status, bank balance, whether do they own a home or not, and so on, because they're likely to behave in a similar way. I'm likely to buy things similar to other people in my age group. I'm likely to behave in a similar way as other homeowners, and so on. So these are naturally used when you build models and when you want to make predictions. But when you start thinking about making predictions about whether a customer will buy this product, we can see that there are lots of other characteristics and other properties about this person that might be of interest. For example, how many of her friends have bought this product? So I'm likely to buy something because I'm in the same age group as someone else, but I'm also likely to buy something if my friend recommends that to me, and this friend could be much older or much younger than me, because I trust my friend's judgment. So if my friend says this is a great product, you got to go buy it, then I'm more likely to buy it. How many of my friends' friends have bought this product? I'm likely to trust my friend's judgment also, perhaps a little less than my immediate friend circle, but I am likely to trust my friend's judgment more than I trust a stranger's judgment. So these are also input that could help make accurate predictions. And is she part of this, is this new customer part of a cluster of people who have bought insurance? And this cluster could be determined in many different ways. And as Alberto just showed in his excellent presentation earlier, you can create a social graph based on different parameters, and they use the time and location of using a credit card and other information to determine a social graph, and from there they determine clusters. So if she is part of, if this new customer is part of this cluster, and if many of them have bought insurance, is she also likely to buy this policy? So the question then becomes, how can we get this information from graphs? And how can we create this, make this as input to our machine learning models? So graphs are uniquely suited for analyzing your data based on connections, as others before me have mentioned here today. So when you model your data as a graph, you can then get the insights into this. For example, if you're able to model the social media network as a graph, you can then identify who are her friends. Did they buy this product? Did her friends buy this product? Is she part of a cluster? And so on and so forth. And the nice thing is almost any data set can be viewed as a graph, because there are always logical connections between data items. As in, if two people are friends, that's a connection. If two people bought the same product, that's a connection, and so on. So graphs gives you a way of connecting different data entities together and to find relationships between them. And here is these are just some examples of graphs. So when you have all of these connections between data entities in your graph, you want to capture like the strength of the connections, how connected they are, and so on, and input that into your machine learning models. And that's where various other things come in, and I'll talk about in the session. But one of the key things that are used is the algorithm output from algorithms. So you can run, for example, degree centrality algorithms to identify how well connected a node is, or if a customer is representing a node, how well connected a customer is to other nodes. That's a degree centrality measure that gives you a numeric measure for how connected a node is. PageRank is another example. It now goes a little deeper than just measuring how connected somebody is. It looks at how important a node is in the graph based on not just the number of connections connecting to this node, but looking at the importance of the nodes that this node is connected to. In other words, you are not important just because you're connected to a lot of people. You're important because you're connected to a lot of other important people. And PageRank is an algorithm which returns a value between 0 and 1. And this is a numeric value that becomes a property of a node in a graph when you run a graph algorithm. And then you can use that in your machine learning models. So you can see here, we can have the raw data, these feature 1, feature 2, feature 3 that are used in creating your machine learning model. You can add additional features that are output from running these graph algorithms, the numeric values you get from running these graph algorithms. You can include that as features when you create your machine learning model to get more accurate predictions. So the goal, of course, is always to improve the accuracy in prediction. And as Gianni was saying earlier, the more data you have, the more accurate your model is likely to be, the more accurate the predictions are likely to be. There's also other advantage, as my friends in machine learning explained to me, is that when you're able to input the connections to the model at the beginning, it doesn't have to discover it by itself, because it is likely that a machine learning model could discover some of these connections by itself. But if you're able to input the connections by looking at your data as a graph, if you're able to identify some connections information and input that to your model, then the machine learning model itself doesn't have to discover these relationships by itself. It could lead to less development time and so on. So the key point is connections can be captured from data. Almost any data can be modeled as a graph. And all of these connections can give you valuable information, additional features that can be used in your machine learning applications. So now with that, let me go to some use cases. So intrusion detection is something that folks have worked on, particularly our colleagues at Oracle Labs who we work with these products. And when you're looking to identify malicious attacks, when you build your models, you're looking at the IP addresses of systems that have been involved in these accounts. You're looking for various patterns in these attacks, and you're looking for various patterns and so on. So you take all of this information and you put them in your model, and then you say, when this new packet comes along from this particular IP address, then you try to say, okay, is this likely to be a malicious attack or not? So what can be done when you model this as a graph, your IP addresses could become nodes in your graph, and your requests and responses between these nodes can become edges in the graph. Then you can look at this subgraph as an entity and run some analysis on these algorithms, like the degree centrality, the page rank, vertex between the centrality, another algorithm for identifying the importance of a node in this network, and so on. Run many of these algorithms to get numeric values associated with each node. And you can take all of these values and input that into your machine learning model to get more accurate predictions based on the pattern. So you're not just looking at individual entities, you're looking at a whole pattern. As in that, in this case, somebody contacted the search engine, was directed to a particular website. There was an intervention there, or redirected to another website. So this whole pattern can be used to make better predictions on whether something is a malicious attack or not. Another example is from healthcare, where you are, let's say you're collecting information about patients and their symptoms, and you want to try and make predictions on what this patient could be suffering from. So when you're looking at this data as a graph, since graph is schemaless and flexible, one of the advantages is you can integrate this with other information available publicly, as in from research papers, from PubMed and so on. So you can have your patients and symptom information. You can also have your other research information or other data coming in from other sources, and you can create this all and create a graph out of this. And how does this help in making predictions is that instead of looking at only the symptoms of a patient, when making a prediction. You can also look at how close this particular patient is to some other patients in this graph, and use that also as input to the model. In other words, you can identify the neighbors this patient has in a graph based on similarity values and other characteristics within the graph. I mean, how connected is this patient to other nodes in the graph? And you can take some information about these neighbors and then include that in your prediction to get more accurate prediction. And the last example is, once again, I'm going to talk about PaySafe. I know we have referred to them a couple of times already. They are a customer, they're a reference customer, so we can talk about them. So they've been using graphs for a while to detect fraud and do a variety of things. And here are some examples from one of the recent sessions. So they model user accounts as vertices and cash transfers as edges. And one of the things they've been doing, among the many things they've been doing, is that they want to cluster their data. And they're clustering by certain properties like the device used, geolocation, IP addresses, and so on. And then they find that, of course, the more connected a subgraph, the more suspicious it gets. So if they find that a particular group of users are tightly connected by either being in the same geolocation area or using IP addresses within the same area or so on, then if they're all tightly connected to each other, then maybe something suspicious is going on. They also use other graph algorithms to identify patterns in money flow. Like if a single user gets money from 20 different users and then forwards money to a single account, maybe there's something they want to investigate further. Or if it's a single user getting money from 50 different users, that's again something they might want to investigate. So they model the data as a graph and get all of these patterns, and then use graph algorithms to analyze this data. So how are they working with machine learning? So one of the big use cases is to identify fraud and identify accounts that have been engaged in fraudulent activities. So if there is a new user that comes along, and there are other characteristics that make this user similar to these known fraudster accounts or suspicious fraudster accounts, the graphs give them an additional way to look at this based on the connections that could be there between this new account and fraudster accounts. For example, is there a connection of a 2-hop distance between them? Or when you look at a graph community, does this user belong to this graph community which already has a bunch of known fraudster accounts? Then that's something they want to, that tells them that there could be something fraudulent about this account as well. So they're able to bring in the connection information and add that to their machine learning models. So this is also known as good vertex embedding. How do you translate a vertex into a value that can fit into your machine learning algorithm? And they found that there are various ways in which they can do this, and they're able to have vertex embeddings that allow them to classify vertices better, find similar segments of users, do better prediction of what kinds of money transfer is going to happen. And overall, they've seen a real improvement in their existing machine learning models. So they find this combination really powerful. So I just want to take a couple of minutes before I finish to talk about how you would start doing this work if you were to work with a property graph. I mean, you could use any database and any machine learning algorithm to combine these technologies. But if you were to use, let's say, the property graph feature in Oracle database, you would have really almost no limits, virtually no limits on your size of the graph. The graph can scale to arbitrarily large sizes. And you could work with tables you have in the database and create a graph. And then we have a a SQL-like query language. If you're using our product, then you would work with a SQL-like query language. And we have an analytics API. There was lots of discussion on algorithms in the last session. So we have pre-built algorithms. We have a Java and a Python API. So just in order to give you a feel for what the product is like, and this is of course available on cloud and on premise. We have a graph database. We also have an in-memory graph server for running high-speed graph algorithms, because some of them get to be quite intensive. We have the APIs to load the data from the database into the server and run graph algorithms and so on. And people often ask and say, okay, I have my data in tables, and how can I create a graph? And I've been saying that you can do that, so I just wanted to quickly show you how this can be done. So if you take a simple table, similar to what PaySafe had, you have an accounts table, you have a transactions table, and you can specify that each account is a vertex, and then each transaction between accounts is an edge. And you can specify that using simple PGQL DDL syntax and create a graph from this table. So within the context of one product, you can create a graph, get some insights into the graph, and then do some machine learning. So when you want to get insights into the graph, and once you've created the graph, you want to run some queries on it. And this is an example of the SQL-like PGQL language that we have, and it has a match clause, you can see, that helps you match patterns in the graph, because identifying patterns in a graph is all about specifying the pattern and seeing whether this pattern exists in the graph that you can use for other analysis. So some of the patterns that you want to find out is, are there cycles in a graph? And some of this value can be used as a feature in machine learning. For example, if a particular node or vertex is part of many different cycles, like in a cash transfer graph, there could be many cycles. And if a particular node is involved in many different cycles, that's valuable information. And that gives you a numeric value that you can make a feature as input to your machine learning model. Similarly, when you're looking at paths, is my node, is this node on the path between these two other entities? That could be a value that you're going to use in your machine learning model. So you would typically run some graph queries, get some insights into your vertices, and then use that information in your machine learning model. And there's a visualization tool for visualizing the results of some of your queries. And the graph analytics algorithm that you can run. So you can run queries to get some insights into the different vertices in your graph. You can run graph analytics algorithms. And we have over 50, if you're using the Oracle product, you have over 50 pre-built algorithms available to detect things like strongly connected communities, ranking the importance of a graph and of a vertex and so on, and finding shortest paths and so on. And these can easily be invoked using a Java API or a Python API to identify key things like this. For example, here is a vertex with a very high betweenness centrality value because it's connecting two clusters. If you take away this particular vertex, your graph could become disconnected. The big vertex in yellow here. So this is an important value. Again, betweenness centrality is a numeric value that can be a feature in your machine learning model. On the right, we have an example of PageRank. Account ID 135 has a higher PageRank than others because of the way it's connected to other nodes in the graph. So if you were to work with graphs and ML in the database, so you run your queries, you run your graph analytics, and then what do you do? So you have your database tables here. And you can, as I explained, you can create a graph for doing this graph analysis, running graph queries. And then once you do that, you can then insert the results back into your database table. Because we have, let's say you have a Java API, you're running your graph queries using a PGQL statement embedded in your Java statements, and you just make a JDBC connection, write the results back to the table. And then you can use these features in any one of the Oracle machine learning algorithms that are available. So I'm just using the Oracle database as an example for a platform, but you could do the similar thing with many different products as well. So create a graph, get the results from graph analysis, insert that back into your data store and use that in your machine learning algorithm. So it's quite simple to get started with this. So I'll just finish off with some additional algorithms that people are talking about intensely and are being used in to evaluate their how much they improve machine learning. So I talked about numeric values and using that in your machine learning models. What can we do? But instead, can we take a specific graph itself, the entire graph and the connections, and use that in a machine learning model? So just to talk to a couple of them quickly, you can create a feature vector from a graph or a subgraph. Like in this example, you're starting with a particular vertex, you're walking, you're pursuing a path from that vertex, and you are you say that I'm going to concatenate the properties that I'm going to that are in different vertices that I'm going to cross in my path, and I'm going to use that as a vector. So you're trying to get a representation for a graph pattern and use that in your model. And here's another example, graph-wise, and there's a lot of debate. If you look, there's a lot of academic literature on this. It's about how can I bring in graphs when I'm working with neural networks? How can I have, in this case, the graph-wise algorithm has a couple of layers that use graph values. So you're going from one layer to the next. They're using some graph feature. They're looking at the neighbors of a vertex and get mean aggregation values from there to go to the next layer. So kind of bringing in graphs as part of the convolutional layers and creating your neural network. So these things from a product perspective, these are things we're planning on including in the product. And this is a topic that is of great interest to a lot of people. So to summarize, to quote PaySafe, graphs and machine learning combination is powerful. And there are many ways in which you can include features that are created by connections in a graph in your machine learning models. It just can help improve the accuracy of your models and automation and so on. I think it just opens up a whole world of powerful analytics that is possible. This, I would like to acknowledge two of my colleagues who helped me with this session. And with that, perhaps we have a couple of minutes for questions.
Thanks a lot, Melli, for the great session. I guess questions are still in progress, so people feel free to write them in the Q&A box. If Melli will not have time to answer live, she can always write the answer by typing or in the Slack channel. She joined it earlier, I guess. Yeah. So feel free also to use the Slack channel. And if you have no question, I guess we have like 2 or 3 minutes before the next and last session of the day.